All right, so for number 13, here's what we know. We know that the spring constant of the spring is 50 newtons per meter. All right, it says initially the spring is at its relaxed length and the block is stationary at position x equals 0. Then an applied force with a constant magnitude of 3 newtons pulls the block in the positive direction of the x-axis, stretching the spring until the block stops. When that stopping point is reached, A wants to know the position of the block. All right, so when I was working through this one in tutorial, I assumed that point A meant the point where your net force is 0, right? Like it seems like it would stop once the force of the spring cancels out the 3 newtons, right? But that's not right. Huh? Here's why. So check it out. So here's our initial point. Okay, so that's at x equals 0, right? And then I'm going to pull it this way with a force of 3 newtons, right? Okay, as I pull it this way, the force of the spring is going to get bigger, right? All right, so at this point, so the entire time that elapsed between here and here, the net force was positive, right? That means it accelerated, right? So by the time you hit this point, yes, your net force is 0, but you're moving this way with some velocity. So now to stop that forward velocity, we need to produce a negative net force. Does that make sense? All right, so it's not actually going to stop until sometime later when your force is 3 newtons and the force of the spring is some big number, which I don't happen to know what it is, but it's some bigger number, right? Does that make sense, you guys? All right, and what we want to know is we want to know what this is at the point where your velocity is 0. Follow? All right, now, with these work and energy problems, your mantra should be identify the important points in the motion, think about what the energy looks like at each of those points, okay? And then ask yourself, did my total energy change or not? If it changed, then it basically is going to boil down to work equals work. All right? So for this problem, what I want to know is I want to know my displacement between this drawing and this drawing, right? Okay, so let's call this drawing 1 and let's call this drawing 2. All right, so in drawing number 1, tell me something useful about the energy. Is it moving yet? Nope. Is there any GPE? Any EPE? No. What's the total energy in drawing 1? 0. So the total energy in drawing number 1 is 0. Good? You know what? I guess maybe I'm worried that we're going to need this other point. I'm going to call this one 2. Oops. I'm going to call this one 2 and call this one 3, just in case we have to go back. I want them to be in order. All right. Now, at point 3, so in this last drawing, is our total energy still 0? No. What kind of energy do we have in that last drawing? Just elastic potential energy. Right? Why? Silly question, but I want to make sure you're all processing it. Why isn't there any kinetic energy? Because it stopped, right? That's what makes this point special, right? That's the point where the box stopped moving forward, right? Follow? Any problems? All right, so I've analyzed my energy. Next question. What do I know about the energy? Is it constant? No. So now we want to think about our non-conservative work. So between these 2 points, what's the name of my non-conservative force? Or where's the non-conservative force coming from? Spring's not non-conservative. Right? Remember, gravity and spring are conservative, right? So the non-conservative force is this, the 3 newtons, right? Good? So there's something useful about this force, it's constant, right? The problem says you exert a constant force of 3 newtons. So the work applied by our non-conservative forces is 3 newtons times x. Right? Because that's how far we dragged it between this point and this point. Follow? Questions? All right. So now what I can do is I can set up an equation. I know that the work done by non-conservative forces is my change in total energy. So 3 newtons times x equals 1/2 kx squared minus 0. Make sense, you guys? This is at the heart of a lot of those problems on the worksheets. That's a big idea. Make sense? Questions with it, with what I did there? Okay. Part of the, so remember you guys, when we started this, we learned 3 different equations for work. The work done by conservative forces is the change in potential energy. The net work is equal to the change in kinetic energy. Why is this not a great option for us here?
The 2 points are 0.
Yeah, okay, so there's no change in kinetic energy. That means your net work has got to be 0. So net work would be determined by the net force, right? Why would we not want to deal with
2 forces? There's a
There you go. Say it again, Joe.
It's not constant.
The net force isn't constant, right?
There's a spring.
Because that stupid spring, the more you stretch it, the more force the spring exerts, that's going to change your net force, right? So this work done by non-conservative forces is our change in total energy. Very, very useful equation. All right? Good, you guys? All right. So I'm looking at 3x equals, what was our k again? 50. So 25x squared, and you can solve it, right? There's 2 solutions. X equals 0, and then if you cancel out an x, you get 3 equals 25x. So whatever 3 over 25 is. What, 0.12?
Yep.
Good?
Can you say then that just like when the force is 6 newtons in that direction, that's when it's going to be stopped, right? Because that's
that does turn out to be true. I don't know that that's obvious. I think it turns out to be true because your force varies directly with that displacement.
yeah.
And I think you could show that it sort of averages out.
Okay.
Yeah, because that would be the point at which your average force from the spring
Yeah,
is
exactly.
-3.
When
So
the
there's your
velocity-
argument.
velocity's constant.
Right. Okay, so that was that. Everybody good up to there?
Yeah.
All right, so this, I think, is going to come up. I would be surprised if that didn't come up again sometime later today. All right, so part B, find the work done by the applied force. Oh, well, that's just 3 times 0.12, right? Force times displacement, right? So 0.36 joules. The work done by the spring. Well, am I going too quick? Are we good with part B?
Yep.
Okay. Part C, what's the work done by the spring? Well, the work done by the spring should be equal to the opposite in the change in potential energy, right? So we gained 0.36 joules of potential energy, so the spring must have done negative 0.36 joules of work. Follow? All right, now, during the block's displacement, what's the block's position when the kinetic energy is maximum? So what am I looking for? I'm looking for maximum velocity, right? Maximum kinetic energy would mean maximum velocity, right? Good, I'm glad I renumbered these. So incidentally, this is a thing that I think we talked about it a bunch at the beginning of the year. Well, no, I guess I'm getting ahead of myself. Anybody have any ideas? When's it going to hit its maximum velocity?
When the net force is 0.
Good, when the net force is 0, right? Because when the net force is 0, that means your acceleration is 0, right? So that's the point where the acceleration switches from being positive to negative, right? So I think that's drawing 2, right? Right? Because after drawing 2, the force of the spring is going to exceed your force and it'll start slowing down, right? So this drawing 2 here, where your net force is 0, represents the point where the speed is maximum. So how do I find out what do we need to find? X, where that happens? Is that what it wants? Yeah, what's the block's position when the kinetic energy is at its maximum? Well, any thoughts? You can do this in one step. I will erase while you think. You guys know that song? It's a jam. It's on all the radio stations. You guys know what a radio is? No, that was a barb at me for being old, because nobody listens to the radio anymore. Okay, how do we do this? How do we find the X when that happens?
This is the radio. This is the AM.
You just told me that the net force has to be 0, right? Are we all good with that for part whatever we're on, D? So what does the force of the spring have to be? 3 newtons. Tell me something about the force of a spring. Some of you forgot it on the last test. F equals negative kx, right? So let's see, we need the force of the spring to be 3 newtons. Our K is 50 newtons per meter. So divide and you get 0.06. So I guess, yeah.
Can you explain why the velocity is at its maximum?
Why is the velocity at its max at that point? All right. I'm going to give you 2 explanations. Tell me which one of these makes more sense for you. Okay? Explanation number 1 is kind of what I already went through, but let's walk through it again to make sure you kind of follow the train of thought. All right? So at the beginning of our setup, oops. The block is just sitting there, right? So right now the net force is 0, right? Then I come along and I pull on this thing with a force. So here's the force of Evan. So Evan's pulling on the box with a force of 3 newtons. Okay? Because my spring isn't stretched at all, the force of the spring right now is 0, right? So it's going to accelerate this way, right? Because my net force is that way. Now, as I stretch the spring, its force gets bigger. So the force of Evan, oops. So the force of Evan is still 3 newtons, but now the spring is pulling back with some force. So maybe it's whatever, 2 newtons. But do you agree it's still going to speed up this way? Right? It's going to keep speeding up that way because Evan's force is still beating the spring, right? So it's going to keep speeding up this way, right? Eventually, you're going to get to a point where Evan's force is canceled out by the spring. So now it stops accelerating. And then as soon as I stretch it a little bit more, then this force gets bigger and slows it down. Cool? Does that make sense? All right, so that's answer number 1. All right, here's answer number 2, which I would like you guys to all understand. This is a thing that came up early in the year, but because I sort of put calc on the back seat for a little bit, we haven't talked about it in a little while. So forget about physics for a minute. Calculus. How do you maximize a function? You set the slope equal to 0, right? Okay. So we're trying to find the point where it hits its maximum velocity, right? So I want to find the maximum of this function, right? Good. So arbitrarily, suppose I had some function for the velocity as a function of time. Slope. What am I doing to find the slope? Take the derivative. The derivative of velocity is acceleration. So what I really want to do is I want to find the point where my acceleration is 0. And if the acceleration is 0, that means the net force has got to be 0, right? So there's your mathy explanation. Make sense? All right. All right. And then finding the kinetic energy is just plug and chug, right, for E? Actually, that's not true. I guess, how would we do E? It's 2 steps, I think.
Well, the highest.
E says find the value of the maximum. Oh, no, I guess this is not as easy as I was thinking it was. The value of the maximum kinetic energy. Huh. All right, let's do it. All right, can I erase? So now we've got 2 points that we care about. Point number 1, we've got a total energy of 0, right? And then point number 2 is this point where we've got our displacement of 0.06 meters, right? Okay. So at point 2, what kinds of energy have we got, you guys?
Kinetic and elastic.
Kinetic and elastic potential, right? So at point 2, my total energy is elastic potential energy plus kinetic energy, right? So that's 1/2 times 50 times 0.06 squared plus 1/2. What's the mass of the block? Do we know it?
Don't know.
What? Who wrote this problem? No, some stupid textbook company. All right, we must not need it. All right, everybody agree with that? Everybody good? Oh, wait. What are we trying to find? We're trying to find the kinetic energy, aren't we?
So we don't need that.
Oh, so I'll just leave kinetic energy in there. There's my problem. All right, so everybody good with that? All right, now, is the total energy at point 1 and point 2 equal? No. So, the work done by non-conservative forces should equal the difference in the total energies. So, what's the non-conservative force is the 3 newtons, right? What's my displacement between my 2 points, you guys? 0.06. Let's see, force is that way, displacement's that way, so everything's positive, we're gaining energy. That's got to equal 1/2 times 50 times 0.06 squared plus the kinetic energy, right? That's TE final minus 0. And then solve for your kinetic energy. All right. So this is a big deal, just like Ron Burgundy. Yeah.
I didn't do this when I tried this problem, but because the force is changing linearly, like the net force and means changing linearly, should you take the average force on the interval to the 0.06 and just do force times distance?
I believe so. You would want net force,
Yeah.
average net force. So yeah, that would work, I think. So your initial net force would be 3, your final net force would be 0, so 1.5. Does that work?
Yeah.
Neat. That's even cooler. All right, everybody good?
So the answer to that was 0.09.
Yep, I think.
Okay.
Yep. Cool. All right, problems with that. All right, that was a long one. I think the other ones aren't quite as long, hopefully. So that's 13. How are you going to put that on a shirt?